In section 7.5, we're going to be solving trigonometric equations. And this is going to involve, for almost all of these, as our last step, looking up some values on the unit circle. So I have right here handy a completed unit circle. So let's go through exactly how to do some of these. So just in general first, our initial goal is to isolate the trig function in the equation. And there's a couple ways that we can do this. We can do this if there's only one trig function in the whole entire problem. We can do this just by using opposite operations. We can get rid of addition and subtraction just by moving it to the other side. We can get rid of multiplication just by moving it to the other side. We can get rid of squares by doing square roots. This is when there's only one trig function. If there is more than one trig function, we may have to do some factoring before we can isolate and use opposite operations. So when you think of factoring, you should be thinking of your quadratic equations and how we solve quadratic equations. So these are usually going to have two or possibly more trig functions. And it could be that it's not two different trig functions. It could be two of the same trig functions, but it's two instances of a trig function that can't be combined. So we might have a sine squared in the problem, and then also just a sine in the problem. And those can't be combined because they're not like terms, because they don't have the same power. It's also possible that you may have to use a trig identity. And you would have to do this if any of your trig functions did not have the same angle. So one of my trig functions had x as the angle and the other trig function had 2x as the angle. I would want all my trig functions to have the same angle. So I would use a trig identity to fix one of them before going on. So there's only one trig function in the whole problem. We can just use opposite operations to get it all by itself. If there's more than one trig function in the problem, we're going to use some factoring to help us isolate it. If we've got some mismatched angles, we're going to use a trig identity to fix that. And our ultimate goal is to get the trig function all by itself so that we have like sine theta equals some number. And if I've got sine theta equals some number, I can go on my unit circle here and see where sine equals that value and give back my answers. Now, if it's not a value on my unit circle, then we would just have to rely on the calculator. But for most of these, they're going to be values on the unit circle. So let's go through some examples. And I'll do a couple of each of them. So let's say we were asked to solve for cosine squared x minus 1 equals 0. And we're solving for x. There's only one trig function in this whole entire problem. So all I need to do is use opposite operations to get that trig function by itself. So I'm going to add my 1 over, and I get 4 cosine squared equals 1. I'm going to divide my 4 over, and I get cosine squared equals 1/4. And to get rid of the square, we square root both sides. Now you need to remember from algebra class that when you use square roots to solve, you've got to put plus and minus in front of your answer. And the square root of 1/4 is 1/2. So our answer is anywhere where cosine is equal to plus and minus 1/2. So if you look on your unit circle, we're looking for angles that have a cosine value of positive or negative 1/2. On our unit circle, the cosine value is the x value. And the y value is the sine value. So we're looking around this unit circle at the x values because our equation has cosine, and I want to know where I have either positive 1/2 or negative 1/2 in the x position. And there are 4 different spots. And we're just doing this in degrees right now. So it looks like I've got 60 degrees, 120 degrees, 240 degrees, and 300 degrees. So x is 60, 120, 240, and 300. You could always check this also. You could plug 60 degrees back in for x if your calculator is in degree mode and see what you get, and then square it and multiply it by 4 and subtract 1, and you should get 0. And you should be able to do that for all 4 of those angles. Find the cosine value for each angle and then square it, multiply it by 4, subtract 1, you should get 0. So again, only one trig function in this problem. We can solve just by using opposite operations to isolate it. The most important thing here, and the one thing that I almost always see people forget, is when you use square roots to cancel a square, you've got to put the plus and minus in front. So let's look at another one similar to this. Let's say that sorry, I'm trying to eat something, but I'm all done. Sorry about that. I want to use a reciprocal function. That might not be such a good idea right now. I don't want these to get too difficult because I know in your homework they don't get too crazy in your homework. They stay pretty basic. We're going to say, yeah, this one's not too bad. We're going to say cosecant squared x minus I'm trying to think if that's what I really want. I think I do. I might regret it in the long run, but we'll see. 3 cosecant squared x minus 4 equals 0. 3 cosecant squared x minus 4 equals 0. All right, so there is only one trig function in the whole entire problem, which means I should be able to solve this with opposite operations. So let's just get the cosecant all by itself. So add your 4 over. divide your 3 over. We get cosecant squared x equals 4/3. We'll square root both sides to cancel the square. And I get cosecant x equals, well, I can do the square root of 4, that's 2, but I can't do the square root of 3, so I'll leave that alone. And you got to do your plus or minus. We don't have cosecant explicitly labeled on our unit circle. So I'm gonna fix this. I'm gonna change it into something that we do have labeled on our unit circle, using an identity, and it's our reciprocal identity. If you flip cosecant, the reciprocal function is sine. And we're allowed to do that as long as we also flip this side. So if I flip that fraction, I get positive and negative radical 3/2. So our answers are the angles that have a sine value of either positive or negative radical 3/2. So let's look back at our unit circle and find anywhere here where sine, which is the y-coordinate, is either positive or negative radical 3/2. And it looks like it's going to be at 60, 120, 240, and 300. We've got y values of either positive or negative radical 2. So x is could equal any of those 4 angles. 60, 120, 240, or 300. And yes, that's the exact same answer we got last time, but it's a completely different equation. There's only so many answers on that unit circle. So only one trig function in the problem. Use opposite operations to get it all by itself. Figure out a way that we can find the answers on the unit circle. Unit circle shows sine and cosine. And then we go from there and look for them on the unit circle. And do not forget to do plus and minuses if you square root something. So the next type of problem that we might see are the problems that have more than one trig function in them. Whether it's the same trig function written multiple times, or whether it's two completely different trig functions. So here I'm going to say solve for theta, because it's not always going to be an x. So on these we said we're probably going to have to factor. So let's look at a couple of examples of these. And the first one that we're going to try is 2 cosine squared x plus sine x. That's not right, sorry. I didn't want to do two different trig functions yet. 2 cosine squared x plus cosine x equals 0. 2 cosine squared x plus cosine x equals 0. I cannot put those cosines together because they are not like terms. One of them has a squared and the other one does not. So we cannot put them together. But because it's equal to 0, we can use a property that we learned in algebra class that says, if I can get this written as a product equal to 0, then I can separate it and say each of them is equal to 0 individually. That's called the zero product rule. And this is how we solve by factoring. So if I can turn this into a product, then I can separate them. And then we can isolate our cosines. So to take something and turn it into a product, that is the definition of factoring. So always look for a GCF when you factor. Do those two terms have something in common? And they do. They both have a cosine. So I'm going to start by factoring out a cosine. If I take a cosine out of each of them, I'm left with 2 cosine x plus 1. So now I've got the left-hand side written as a product, and it's equal to 0. So I can now separate them and say either cosine x equals 0 or 2 cosine x plus 1 equals 0. Now this guy is ready to go. I'm ready to look at my unit circle and get an answer for him. But on this one, I've got some opposite operations to do still to get cosine by itself. I need to subtract the 1 over, and I need to divide the 2 over. So on that second equation, we get cosine x equals negative 1/2. So we're looking for, I said I was going to use theta, didn't I? And I didn't. Sorry about that. I did not even use my theta. We'll just change it to x. We are looking for any angles where cosine is either 0 or negative 1/2. Any angle that has a cosine value of 0 or negative 1/2. So we're going to look at our unit circle. Remember, on the unit circle, the cosine values are the x values. So scan your x values. We're looking for x values of either 0 or negative 1/2. And I had to go off the screen a little bit. There are 4 of them. We've got 90, 120, 240, and 270. 90, 120, 240, and 270. Cosine is equal to 0 at 90 and 270. It's equal to negative 1/2 at 120 and 240. So we had to do a little bit of factoring to get that one to work. That one was some fairly easy factoring because it was just a GCF factoring. But the factoring could get a little bit harder. So another example with some factoring. This one is not difficult factoring, but if you look at the problem, it looks much more difficult to start with. And you'll see why in just a second. This problem is really no different than the last problem. No different at all. We are going to get a different answer, slightly different answer. But this one looks different because it's got 2 different trig functions. So I said earlier that you may have to do some factoring if you've got 2 or more trig functions. And I said, now those might be the same trig functions and they just can't be combined because they're not like terms, or they may be 2 completely different trig functions. So in the first example we did here, it really was the same trig function, but we just couldn't combine them because they were not like terms. Now in the second example, it's 2 completely different trig functions. But again, the only way to isolate these guys is to factor it. We've got to separate them into 2 separate equations somehow, and then be able to isolate the sine and the cosine individually. So what I'm going to do is always start factoring with GCF factoring. See if those 2 terms on your left have something in common. And they do. Both of these terms have a sine. So I'm going to factor out sine x. And if I pull sine x out of both of them, I'm left with 2 cosine x plus 1. And now that I've got the left-hand side written as a product equal 0, I can set them equal to 0 individually. Now, the first piece, I'm ready to go to the unit circle and figure out some answers for. The second piece, we've got some opposite operations still to do to isolate the cosine. So we subtract over our 1, divide over our 2, and we get cosine equals negative 1/2 again. So we're looking for anywhere where either sine is 0 or cosine is negative 1/2. So we're looking for either sine equals 0 or cosine equals negative 1/2. So I'm going to go to the unit circle. Let me get rid of my old marks. Either sine equals 0. Sine is the y coordinate. So there's a sine of 0. There's a sine of 0. And those are the only two. And then cosine equals negative 1/2. Cosine is the x coordinate. Cosine equals negative 1/2 there. And cosine equals negative 1/2 there. And those are the only two. So there's my 4 answers. And if we're doing this in degrees again, identify those angles. That's 0 degrees, 120 degrees, 180 degrees, and 240. So 0, 120, 180, 240. So again, just factoring and just GCF factoring. So this next one, we're going to answer in radians, just because I want to give you a mixture of problems. So we're not going to put our answer in degrees, we're going to put our answer in radians. And the factoring on this one is going to be a little more difficult. And we are going to run into a different type of problem here. It's going to be a little bit trickier. So let's see what happens. We are going to say that cosine squared x plus 2 cosine x equals 3. Cosine squared plus 2 cosine x equals 3. Now, don't automatically jump to GCF factoring, because that property I showed you up here only works if it's equal to 0. This equation is not equal to 0, it's equal to 3. So the first thing we need to do is subtract the 3 over, so that it's equal to 0, and we can solve it by factoring. So now there is no GCF on the left, and this equation is quadratic in form. We're going to split it up into 2 binomials. Since it's cosine squared in the front, it's going to split up into cosine and cosine. And we're looking for 2 numbers that multiply to make negative 3, but add to make positive 2. They multiply to make negative 3, but they add to make positive 2. And that's going to tell us what numbers to write in the back of our parentheses. And that's going to be a plus 3 and a minus 1. So this is quadratic factoring. And now that we have the left factored and it's equal to 0, now we can separate them. So either cosine x plus 3 equals 0 or cosine x minus 1 equals 0. So now we still need to isolate our trig function. Either cosine x equals negative 3 or cosine x equals positive 1. So we've got two things to look for on our unit circle. The cosine, in the cosine position, we want to look for negative 3 or positive 1. So the cosine position, remember, is the x position. We are looking for negative 3 or positive 1. So there's positive 1. And then work your way around. There is no negative 3's on here. And there's no other place where there's a positive 1. There's only one answer to this problem. And unfortunately, I picked a bad one to do in radians because the answer is 0. And whether we use degrees or radians, the answer is still 0. So we're going to do another one in radians. But the answer is just 0. X equals 0. This is never going to happen. Cosine of x is never going to equal negative 3. If you look on your unit circle, we can't ever find it. And that's because the domain of the cosine function, excuse me, not the domain, the range of your cosine function is negative 1 to positive 1. The only answers you ever get back from a cosine function are between negative 1 and positive 1. You will never get back negative 3 as the answer to a cosine value, ever. That's why we can't find it. And then for this one, the only time this happens is at 0 radians. So just one answer. Let's try another one like this where we have to do that trinomial factoring. Let's do this one also. No. I just want to make sure I pick one that works out well. But I don't want to use any identities yet. We're not ready for that. And I want to make sure we can use the unit circle. So we're going to do sine squared theta minus two sine theta plus 1 equals 0. Sine squared theta minus 2 sine theta plus 1 equals 0. So it's a trinomial. We are going to have to factor this. We can't combine those sine terms because they're not like terms. Somehow we need to separate them. And the way that we separate them is with factoring. So the sine squared in the front is going to be separated into sine and sine. And then for the back part of the factoring, we're looking for two numbers that multiply to be positive 1, but add to be negative 2. And the only pair of numbers that does that is minus 1 and minus 1. So now I've got two things multiplied together equals 0. That means one of them is 0. Sine theta minus 1 equals 0. Sine theta minus 1 equals 0. Oops. And we're going to isolate our trig functions. They both come out as sine theta equals 1. So we're just looking for an angle that has a sine value of 1, and we're going to do this in radians again. We're looking for an angle that has a sine value of 1. Remember, the sine value is the y-coordinate. So we're going to scan our y-coordinates. There's 1. Scan your y coordinates. The one down here is -1. We don't want that. There's only one answer, and we're doing this in radians, so our answer is pi over 2. Theta is pi over 2. So you may have to do some trinomial factoring to isolate those trig functions as well. If you've got multiple trig functions in the problem, they could be the same trig function with different powers, or it could be two completely different trig functions. Now, some of the much more difficult problems require trig identities, and I will show you a couple of those really quick to finish up this video. So we want to solve for x. I've got sine of 2x times cosine x plus sine x equals 0. Sine of 2x times cosine x plus sine x equals 0. So there's a couple of things you should notice here. There are two different trig functions. There's sine and there's cosine. When we saw that type of problem earlier, we talked about factoring the sine out. So when that pops in your head, factoring the sine out, the next thing you should notice is these sines are not the same because they've got different angles. If there are different angles, you need to use a trig identity to get them to match. So I am going to use my double angle identity here to fix this one. So sine of 2x is the same thing as 2 times the sine x times cosine x. Sine 2x can be replaced with all of that, and then everything else is going to stay the same. And we'll go from there. So now if I multiply these together, I'm going to have 2 times sine x times cosine squared x plus sine x equals 0. Now all of my angles match. I still have two different trig functions, and both of my terms have a sine and the angles match. Now I can factor a sine out. I get 2 cosine squared x plus 1 equals 0 after I factor the sine out. Now the left-hand side is a product, and it's equal 0, so I can set them equal to 0 individually. So we are either looking for an angle where sine is 0, and on that second equation, we've got a little bit more algebra to do. We are going to run into a problem though, because I'm going to take the square root of -1/2. Have we talked about complex numbers yet this semester? No, not at all. We have not talked about complex numbers inside of trigonometry. The square root of -1/2 involves i's. And there are no i's on our unit circle. This isn't going to happen. We get cosine of x has got i's in it. Not possible. Not going to happen. That gets thrown away. So really all we're looking for is where sine x equals 0. So we're going to go to our unit circle. Sine is the y coordinate. And we're going to scan the y coordinates for 0. So go around, and we've got two answers. We've got 0 and pi. X is equal to 0, and pi. So before we could work this problem, we had to get rid of that mismatched angle. Since it was 2x, 2 means double, we did a double angle identity to replace it with some regular x's, and then we could go from there. And I'm going to do one more. We haven't really done much with tangents, and I was kind of avoiding them because we don't have tangent values on our unit circle. I have a feeling, though, there's some tangents in your homework, so I don't want to avoid them altogether. So let's jump into some tangents. So I'm going to do one more. Secant squared x minus 2 tan squared x equals 0. We are going to solve this trig equation. Interesting. So, secant squared x minus 2 tan squared x equals 0. That would be a whole lot nicer if there wasn't two different trig functions in there. But there are identities that link tangent squared and secant squared. Anytime you see squares, you should think Pythagorean identities. All of your Pythagorean identities have squares in them. So take a look back at your Pythagorean identities, and one of them says that tan squared plus 1 equals secant squared. I'm going to use that. I'm going to replace secant squared with tan squared plus 1. I'm going to see if that's going to help me. I think it's going to. At least then, there will only be one type of trig function in the problem, instead of two different types of trig functions in the problem. So again, anytime you're dealing with any sort of trig simplification problem, trig proof, trig equation, if you're dealing with squares and you want to try to fix it or change it, you should always think about using your Pythagorean identities, because all of your Pythagorean identities have squares in them. So secant squared is going to get replaced with tan squared plus 1. The rest of it is going to stay the same, and let's see where we can go from there. Well, I've got some like terms now. This is a tan squared and this is some tan squareds. I've got one of them minus two of them. So technically I've got a negative one of them. Perfect. Now there's only one trig function in the whole entire problem, and I just need to do opposite operations to isolate it. So I'll minus my 1 over. I'll divide my negative 1 over. I get tan squared equals 1. I'll square root both sides, and I get tan equals positive or negative 1. If you're going to square root to help you solve, you've got to put plus or minus in front of it. So tangent is equal to positive or negative 1. This is an easy place to remember on your unit circle, because tangent is sine over cosine. And the only time a fraction comes out to be 1 is when the top and the bottom match. So we really could easily find these angles on our unit circle, because we're looking for where the sine value and the cosine value are the same. Now, we don't care if the signs are the same, because we'll take the positives and the negatives. We're just looking for places where the sine and the cosine have the same value. That way, when we divide them to get tan, it always comes out to be 1. So tangent is positive or negative 1 anywhere sine and cosine have that same number for them. So x is going to be equal to, let's go over to our unit circle. And let's look through here and see where the sine and the cosine values look the same. Now their signs might not match. One might be positive and one might be negative, but other than that, it's pretty much the same number. So 1 and 0, those are not the same. Radical 3 over 2, 1 over 2, those are not the same. Radical 2 over 2, radical 2 over 2, those are exactly the same. Perfect. If I were to divide one of them by the other, even though it looks ugly, it's the same exact number. It's going to equal 1. This one is the same as this one. Pretty much, just flip-flopped. They're not the same. 1 and 0, those aren't the same. It looks like it's going to be anywhere we have that radical 2 over 2, radical 2 over 2, because we don't care about the positives and negatives. We said we're going to take the positives and the negatives. So it's all these spots. All these middle spots for each quadrant. This is where tangent is equal to either positive 1 or negative 1. Because this is where sine and cosine have the same values. So pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So as you're working these trig equation problems, you absolutely need to have a unit circle handy. If for some reason it's not a value on the unit circle, first I would double check your work, because most of them are. Reread the directions. A lot of you are not reading the directions for the problem, and you're only getting it wrong because you're not answering it the way that they're asking you to. So if the directions specifically say use your calculator and round to so many places, then wonderful. Just we could just type this in the calculator as x equals tan inverse of 1 and tan inverse of negative 1 and so on. So especially if this was some weird number that we couldn't find on our unit circle. So read the directions. If they want exact answers, you have to use the unit circle. If it says you can use your calculator and you can round it to so many places, then we would just use the inverse function because we're trying to solve for an angle. And the trig equations are the only thing that's covered in section 7.5. So I hope that's helpful. And before you have to take your test next week, I'm going to go back and I'm going to make videos for section 2 and section 3 as well, for you to review and hopefully help you on your test.